Okay. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL TA for the course Introduction to Probability Theory and Statistics. This course is offered by Professor S. Dharmaraj. He is a professor in IIT Delhi. Okay, so this is the third week of a 12-week course. And in the previous 2 weeks, we've discussed about the probability, the definition of probability, and axiomatic definition, Borel field, sigma algebra or sigma field, and conditional probability, Bayes theorem, etc. Now, uh, in week third, we will discuss about the moments and inequalities. In third week, we will discuss about moments and inequalities. Okay, and in this particular topic, we will like able to calculate the mean and variance, which are usually known as first and second order moment, and then higher order moments. And there are some inequalities are there. Like we will discuss about the meaning of inequalities. It mainly gives the bounds, either upper bounds or lower bounds. Okay, and it involves the moments. Okay, so that's why it is called moments inequalities. And at last, we will discuss about generating function. In generating function, we have like probability generating function, moment generating function, and characteristic functions like probability generating function, PGF, moment generating function, MGF, and characteristic function. We will discuss how to calculate these or how to construct the PGF, NGF, and CF, and how to like calculate the how to calculate the probability or the expected value from these distribution, these functions. Okay, so let's have a brief recap about the third week course, like mean or expectation. Okay, let's start with mean or expectation. Like mean is defined as the average. It is also known as like average. Okay, mean, average, expectations. These are all the synonyms for one statistical quantity. Like x is a random variable. Like let x be a random variable. Okay, on a probability space omega, field f and p. So this is a probability state space. So if x is discrete or continuous random variable, then we have different like approach. Either we use summation or integration. So let's start with the discrete. Suppose x is a discrete random variable. In that case, we define the mean or the expected value of x denoted by this. Okay, the notation is XEX, expectation of x. It is defined as summation over x x into probability of x equal to x. Here, this actually the mass. Also, x is continuous random variable. Then we define the expected value of x by replacing the summation side with the integral sign x into fx dx. Here, this is the probability density function of the random variable x. Here, the value of x, we can also like write x from minus infinity to, okay, x from minus infinity to infinity or some other values. That's why I am directly my screen. Can anyone confirm?
Yes.
Okay. Okay then. So these are the formula for the calculation of expectation. Also, there are condition like this is only defined provided the condition like summation of modulus value of x, like absolute expectation exists. Okay, then this gives the mean or mean value of the random variable x. Okay, so x is equal to x, here the range of x, or in case we will discuss about the continuous distribution, then it is x fx dx. Okay, if these are like the convergent or have a finite value, then these quantity calculated by either summation over x into px or integral over x into fx dx is termed as mean or average value or expected value of a random variable x. Okay, like for example, we can see like we have a x is a random variable. Suppose x is a random variable with PDF. Suppose we are given PDF of x is like this 1 upon pi and 1 plus x square. These are already discussed in the lecture. I'm just uh, making a brief notes. Okay, for the range of x lies within minus infinity to infinity. That means it is belongs to a real number. Then in that case, we need to calculate the expected value of the random variable x. But first we need to check that the since it is a continuous distribution, so we take the integral over minus infinity to infinity and the absolute expectation fx dx. And since it is a like modulus and x 1 plus x square is there, so it is an even function, so it comes out to be 2 by pi and then 0 to infinity x upon 1 plus x dx. And everyone know like na, this is not a convergent, this is a divergent actually, which comes out to be 0. Okay, so since it is not like we are not able to find the finite value for this quantity, so we say that we are not able to calculate the expected value of the random variable defined here. Okay, so for this PDF, we are not able to calculate the expectation of x. Like in a similar manner, we can take another example. Like if we are given a random variable x such that 2 e to the power minus 2x when x lie within 0 to infinity and 0 otherwise. Okay, so it is also a PDF. It is a continuous PDF. Okay, so again, we will check minus infinity to infinity mod of x fx dx, which comes out to be like minus infinity to infinity, mod x, okay, 2 into e to the power minus 2x dx. Okay, and since minus infinity to 0 and 0 to infinity, so we can directly write like this, equal to 0 to infinity x into 2x, 2x x into twice of e to the power minus 2x dx, and after solution we will get its values half. Actually it is a convergence series which is a finite value. So like we are able to calculate the random variable x for which the PDF is given in this particular equation, suppose 1. Okay, so actually it is a exponential distribution. It is the PDF of the exponential distribution. So its mean and variance are already well defined. Okay, so here in first case, the absolute integration is not possible. And in the second case, it is possible. So in the first case, the expected value of the random variable is not, like we are not able to calculate. And for the second example, the expectation of the random variable x can be calculated. Okay. Also, like we have a discrete random variable as well, like the next example. Suppose we have a random variable. Okay, let me write it. Suppose like let x be a discrete random variable with probability mass function defined like this. Okay, so it's take 1 by n or 0. And the value 1 by n occurs when x equal to x1, x2, x3. That means the probability only exists at a jump point and 0 otherwise. Okay, so now again we first check like summation over x. Okay, and x or over I, let's write I, xi, probability that x equal to xi. Okay, and we need to take the modulus value so that we are like check whether it is a finite value or not. And it can be written like this: summation modulus value of xi into 1 by n I, and after solution we will get 1 by n since it is a constant, so it comes out from the summation. So then it is 1 by n and it is summation mod of xi. Since it is a positive number, okay, x1, x2, x2, it is a positive number and divided by n. So that must comes to be a finite value, maybe a very large number, but it comes out to be a finite value. So it is a convergence series, or we can say that we are able to calculate the expected value of the random variable x defined in the equation. For example, we say it is equation 2. Okay, and also the expected value here is nothing but 1 by n summation of, then we can replace the mod summation x. Okay, and it can also be like some people know that na, this is nothing but average. Average is defined as the sum of observation upon number of observation. So here the sum of the observations are x1, x2, x3, and the total number of the observations are n. So sum of the observation divided by the number of observation. Okay, so this is the case for under discrete random variable. Okay, now we have some remarks for the discrete random variable. The first remark is, suppose we have a scalar quantity or constant, then the expected value of a constant is always a constant. Okay, where alpha is a constant. And the second remark is like, suppose we have the expected value of x is given. Okay, then expected value of ax plus b is defined as a times of expectation of x plus b. Okay, so you can like, it is a linear, it holds the linear property, expectation holds the linear property. Here we can see this. Okay, also okay, we have some more, like x is a random variable. Suppose let x be a random variable, and suppose y equal to g of x is a function. Okay, is a y is a function of x, so it is also a random variable. Then the expected value of g of x, since x is a random variable, y, which is a function of x, is also a random variable that we have discussed in the previous class, week second. Okay, so the expected value of gx is defined as like simply summation over x, g of x, probability that x equal to x, in case we are dealing with discrete random variable, and or we can define it like g of x, the PDF of x dx, in case we are dealing with continuous random variable. Okay, so if y is a function of x, then the expected value can be defined in this manner. Okay, also like suppose we have one more, like x is a continuous random variable. Suppose x be a continuous random variable. Suppose x be a continuous random variable with CDF with cumulative distribution function. The CDF capital Fx, which we usually denote Fx, and if expected value of x exists. Okay, if these condition follows, then we can define the expected value of x as a integral over 0 to infinity 1 minus fx of x dx, and minus of, that comes out to be minus infinity to 0. It is fx dx. This is one more formula to calculate the expected value of a random variable x when we are given the cumulative distribution function. Like either we can first differentiate the distribution function to find the probability density function, and then with the help of those probability density function and the formula that we have discussed above, we are able to calculate the expected value of x. Or we can directly calculate with the help of this formula when we are given the cumulative distribution function. Okay. Also, like we have also discussed like variance. Okay. The mean, we have discussed about the mean, the expected value, which is also like we can say the first order moment. Okay. There are two different kinds of moments actually. One is central moment, the other one is non-central moment, or we can say that the moment about the origin or the moment about the end. Sorry, the moment about the origin, the first one, which is called non-central moment, and the moment about origin, about mean, which is known as usually we call it as central moment. Okay, so the moment about origin, which is a non-central moment, is also known as expected value of the random variable x, is also known as the mean or expectation of x. Okay, but now we will discuss about the variance. Okay, usually we denote like this, variance of x or variance of x, and some other notations are also used. Okay. So variance is defined as like it mainly gives the scatteredness. Okay. How the data or the random variable X is scattered. Okay. This can be measured with the help of variance. Okay. It is a measure of dispersion actually. Okay. Which quantify the measures like the spreadness of the data. So suppose we will discuss about this now. Suppose we have a random variable X. Let a random variable X, like let X be a random variable X with expected value of X, like we can usually denote it either mu as well. Okay, expectation of X, which is also we usually use mu. Okay, exist. Suppose we have a random variable X and the first expectation exists. Okay, then the second order moment, then the second order moment about the mean. Okay, this is called the variance actually. Okay, and it is defined as like variance of X, expected value of X minus mu whole square. Okay, so this is defined as a second order moment. Also, there is one note. There is one more note. Like if we are defining the variance and if the first order moment is not defined, then we are not able to define the second order moment. Actually, if the first order moment doesn't exist, if the first order moment doesn't exist, then we cannot define we cannot define the second order moment. Okay, then we cannot define the second order moment. It is also because like here we see that variance of X is expected value of X minus mu whole square. Okay, A minus B whole square equal to A square minus 2AB plus B square. So we can expand X square minus twice of mu X plus mu square. Okay, so expectation occurs linearly as we have discussed above. So expectation of X square minus twice of mu is a constant. So it comes out from the expectation. Okay, and mu square. Since it is a constant, so expectation of mu square is mu square. Okay, so it comes out to be like expectation of X square minus 2 mu, and expectation of X, we have already like mentioned, expectation of X is mu. So with the help of those 2 mu square plus mu square, and after simplification, we are able to calculate the variance of X as expected value of X square minus mu square, or expected value of X square minus expectation of X whole square. And since if expectation of X does not exist, since this quantity does not exist, then in that case, we are not able to calculate the variance as well. Okay. And this is also one of the formula to calculate the variance. Okay, because this may sometime in some of the numerical, this may have some, we need to like calculate some other terms and maybe tedious, then in that case, we directly use this the last, we directly use this formula to calculate the variance of a random variable. Okay. Now let's calculate the variance from the previous example as well. Like we have discussed x as a random variable. Such that the PDF, it's a continuous random variable, and the PDF we have defined above is twice of e to the power minus 2x when x lies within 0 to infinity and 0 otherwise. Okay, so this is the PDF we are given, and we need to calculate the variance of x. Okay, so in that case, variance of x, okay, we have already discussed now the mean of this particular quantity. Yes, there here like the mean is 1/2. Okay, so with the help of expectation of x is 1/2. So with the help of this, since expectation of x is equal to 1/2, we have already solved above. Okay, so with the help of these, now variance of x equals actually expectation of x minus mu whole square. Okay, so expectation is defined like this: minus infinity to infinity x minus mu whole square into fx dx. Okay, and since it is a actually it is a continuous exponential distribution, and we have already known the it's we will discuss it in later class actually, but here just here x actually follows exponential lambda. In that case, expected value of x is 1 by lambda, and variance of x is like 1 by lambda square. Here lambda equal to 2 is given. Okay, because the PDF of this is lambda e to the power minus lambda x. Okay, and lambda replace 2, like we have taken the value of lambda as 2. So the mean is 1 by lambda, 1/2, and variance is 1 by lambda square, which comes out to be, like after solution, we will check, it comes out to be 1/4, which is a fixed or finite quantity. Okay, so we will discuss this thing as well. Now there are some more properties or remarks related to variance. So let's discuss those things as well. Like variance of any constant is, sorry, like we have discussed, expected value of a constant number or a scalar is the number itself. But in case we check the variability, then the variance of the constant is nothing but 0. Okay, here alpha is a constant. The second one is like variance of ax plus b. Okay, variance of the linear combination of the random variable is a square variance of x only, because plus variance of b, and b is a constant, so 0, and the scalar multiplied with the random variable is comes out from the variability as its square form. Okay, because here in the formula, x minus mu whole square is there. So this is the second property. Okay, and yes, also there is one more property: variance of a random variable x is always either greater than 0 or equal to 0. Okay, so it is a positive or non-negative quantity. Okay, So these are mean and variance. Now we will discuss about higher order moments. Okay, higher order moments. Till now, we will like calculating either first order moment or second order moment, and then the higher order moment. That means the nth order moment about me. About mean, which is also in general term we say that it is central moment. Okay, and it is defined as like suppose x is a random variable. Okay, and nth order moment about the mean is defined as expectation of x to the power n, which is also denoted as mu n, and for n equals 1, 2, 3, and if we are taking it 1, then it comes out to be like the first order central moment. So mu1 is defined like this, na? Expected of x minus mu. Okay, expectation of x minus mu. Here we have used the n script. So, so these are the nth order central moment, the formula for calculating the nth order central moment. Okay. Similarly, uh, non-central moment, it is also defined, and it is mainly or usually denoted by mu and dash. Okay, and the formula for this is expectation of xn, or non-central moment is also like known as central, like moment about origin. So x minus 0. So that's why it is termed as like non-central or x to the power n. And similarly, it is defined like this for n equal to 1, 2, and so on. Okay. So these are the cases. And also, if we have already discussed, na, if you remember, like variance of x is actually expected value of x minus mu whole square. That means it is a second order central moment. Okay, and we have also like expand this formula, and which is equivalent to expected value of x square minus expectation of x whole square. So this implies variance of x, which is second order moment about the mean, can be like denoted as mu2. This can also be mu2 dash minus mu1 dash whole square. So like we can formulate or make equations for central and non-central moment as well. Okay, we have a formula actually. We can directly write the formula. Now we have some theorems, like if x is a random variable such that non-central moment exists. Okay, let me write. These theorems are actually treated as a property. Now we are not going to prove the theorems, but the theorems statement are used as a property. Okay, so like if x is a random variable, okay, such that mu and dash exist, means nth non-central moment exists, then like mu r dash exists for all r is less than s. n. Okay, that means if a higher order moment exists, then the lower order moment already exists. Okay, so if higher order moment exists, then the order which is less than that higher order also exists. Okay, this is one of the theorem. Also, there is one more theorem. We are not going to like prove these, but yes, these are the properties. Also, suppose we have a random variable x whose nth order moment exists, then we can like make a relationship between the non-central and central moments. And let me write, let x be a random variable whose like nth order moment exists. Then the central order moment, a central nth order moment mu n is defined as like summation over k from 0 to n nck mu to the power, sorry, mu k dash. Okay, the and that is non-central moment. The non-central kth order moment mu k dash and minus of mu1 dash to the power n minus k. So with this star, we are able to make a relationship between non-central moment and central moment. Put the value of n equal to 1, 2, 3, and so on. We are able to calculate the central moment with the help of non-central moment. Okay. This can be like easily solved actually with the help of binomial expansion. Okay. Like if mu n equal to expected value of x minus mu to the power n. Okay, expectation of x minus mu to the power n. So a minus b whole square. Oh, sorry, a minus b power n. Using the binomial expansion, and after simplification, you will get the equation star. Okay. So these are the relationship between non-central moment and central moment. Okay. Now suppose we have some questions as well. Actually, we will discuss about the normal distributions in later class. So we will like solve these questions in that class. Now next topic is inequalities. Okay. Look, inequalities are used where we do not have the whole information, like the random variable x follows which type of distribution. Suppose we don't have these kind of information and we have some partial information only. Okay, then there, with the help of those partial information, we are able to like make a bound or create a bound. Okay, so inequalities is only used there to like provide us a bound, either upper bound or lower bound, and maybe sometimes the whole bound, but still most of the cases we get some bounds. Okay, so we are like discussing two, three or four inequalities here. The first one is Markov's inequalities. See, Markov inequalities, when we have only the information about the average value or the expected value of the random variable, then with the help of those value, we create some lower or upper bounds with the help of this Markov inequality. Actually, we have upper bound actually here. Okay, so like I'm just telling the statement and writing the only the final answer. Okay, final inequalities actually. Suppose we have a random variable x here. We have a random variable x here, and this random variable x is actually positive. Okay, positive. So this random variable is a non-negative random variable actually, because x is greater than or equal to 0 comes out to be 1. The probability of x is greater than or equal to 0 is comes out to be 1. That means it is a non-negative random variable. Okay, so if this quantity holds, and also since we are discussing about the expectation, so expected value exists. If these condition holds, then Markov have given a inequality that probability that the random variable x will take value greater than or equal to t is less than or equal to the expected value of x divided by the point. Okay, so this gives a bound actually, like the probability value of x is greater than t, either equal to this value, expected value of x divided by t, or less than this. So it gives like upper bound. We have the upper bound. Okay. So we have an upper value. The probability either reach to this point or it may less than this. Okay. So this is the Markov inequalities. And the second inequalities will be like Chebyshev's inequalities. Okay. Okay. Chebyshev's inequalities, suppose we have information regarding the average value and the variability. That means mean and variance both are known and the distributions are not known. Okay, that we do not know about the distribution, which type of distribution the random variable x is following, but we have the information that the random variable x has mean and variance. Okay, then with the help of these mean and variance, we are able to like construct a inequality. And this one is given by Chebyshev's. Okay, so that's why it is called Chebyshev's inequality. So again, x is a random variable. Okay, and expectation of x, which is also like usually we denote with the mu, and variance of x, which is denoted as sigma square. Okay, these exist. These quantity exist. Then for a arbitrary small value, epsilon, which is greater than 0, okay, the probability that x minus mu, okay, the difference between x and here the random variable is x. Okay, is it? Okay, sorry. Here the random variable x and the mean value of this x is mu actually. Okay, so the difference between the x minus mu, the modulus value is, okay, let me write general form first, then I will replace this with mu. Okay, then the probability that x minus c is any constant actually. Okay, x minus c is greater than or equal to epsilon. This probability value is always either less than or equal to the expected value of is there any question? I'm audible, na? Like my voice is audible, na?
Yes, sir.
Okay, thank you. Okay, so this comes out to be like expected value of x minus c whole square and it divided by epsilon square. Okay, and we in particular suppose x c comes equal x, sorry, mu. Suppose we take the value of mu as c. Okay, then in that case, this is x minus mu greater than or equal to epsilon. This gives expected value of x minus mu whole square upon epsilon square. If you see x minus mu whole square, the expected value of x minus c whole square is nothing but variance of x. Na? We have already discussed this. Or variance of x can also be like denoted by sigma square or variance of x. Okay, so this is the Chebyshev's inequality. There are many form of this, like suppose it's less than and then this. Or if we write is like probability that modulus value of x minus mu greater than epsilon. Say 1 minus, we use 1 minus this quantity. 1 minus variance of x and divided by epsilon square. Okay, these two are actually similar if you can see. These two are similar, just greater than and less than. So we use the like property of complement of probability. Okay, the complementary event. Okay, so this is the Chebyshev's inequality. Like we have questions related to this. For example, let's give one example. Okay, suppose X be a random variable. Suppose we are given X be a random variable with mean, with expectation of X or mean is 1 by 2 and variance of X is 1 by 12. Okay, now we need to find the lower bound for. Now the question is find the lower bound for the probability that X minus half is less than twice of 1 by 12. Okay, using the Chebyshev's inequality. So here, like we can see, na, just we need to compare only actually. So from the okay. So like we need to choose those distribution for which the expected value of X will be like what? This quantity, this quantity. So 1 by 2, 1 by 2, and the variance of X will be like 1 by 12. Okay, these are given. So we need to find that distribution only. Okay, so okay, let's create a function. Actually, these are already defined. So we will be writing like this. Once we are able to like calculate the seed well-defined known discrete and continuous distribution, and we are able to calculate the moments and other statistical characteristics of those well-defined distribution, then we can understand all these things. But here, like here, suppose X lies between 0 to 1 or 0 otherwise. It is actually uniform distribution with parameter 0, 1. This is the PDF for there. Okay, and for uniform distribution, if the PDF of this like this, then expected value of X is A plus B by 2. Here A equal to 0 plus 1 by 2 comes out to be 1 by 2. And variance of X is like B minus A whole square upon 12. That is 1 by 12 after solution. Okay, so here we can directly use the property of the uniform distribution. But with the help of this, if you see, this is the average value and this is the standard deviation. Okay, there are one or two more forms of this actually. We will solve this with the help of question. Okay, I'm just recapitulating those things that I've discussed in the previous lectures week. Okay, now we have one more theorem or one more inequality, you can say. Jensen's inequality. Okay, so Jensen's inequality actually gives, suppose X is a random variable. Okay, X is a random variable with expectation of X exist, and let G be a convex function. Okay, G be a convex function. In that case, then this inequality told us like the expected value of G of X is always greater than or equal to the function operated on the expected value of X itself. Okay, so this gives the Jensen inequality, or this inequality is known as Jensen inequality. Okay, you can say like one example, we can see this. Suppose gx, we have a random variable x and we have a gx is equal to x square. In that case, then expectation of x square is always greater or equal to expectation of x whole square. How to like say this? Can anyone told me why I've written this line? this particular line is written directly, and what is the reasoning behind this? Can anyone remember or tell me how I can write this? Look, it's very simple, na? If you remember the previous formula, uh, since variance of x is what? Expectation of x square minus expectation of x whole square. Okay. And variance of x is either greater than or equal to 0. Na? So if we like merging these two, then we will find na, expectation value of x square is either greater than or equal to expected value of x whole square. So from there, I am writing this line actually. Okay. So there is one more examples are there actually. With the help of those, I can prove this particular inequality, Jensen inequality, but I think one is sufficient. Okay. And there is one more inequality is there. Lyapunov's inequality. Maybe like in this inequalities, again, suppose we have a random variable x. Okay. And with we define bn, a random variable bn, which is actually defined as the expected value of xn. Okay. And this is actually defined. It is a defined like it is a finite value, so it is exist. Okay. And then any for any then for any arbitrary k, and k lies between 0 to n, we can write this beta k minus 1 to the power 1 divided by k minus 1 is less than or equal to beta k power 1 by k. Okay, this is the Lyapunov's inequality. These we will use in higher classes actually, but it is also one of the inequality used in probability theory. Okay. So up to this point, we will discuss about moments, higher order moments, and inequalities. Okay, now we will discuss about the generating functions. Okay, and the first one is probability generating functions. Okay. Probability generating function, also abbreviated as PGF. Okay, look, the definition is like let x be a non-negative integer valued random variable. X is a non-negative integer value random variable. Okay, so that means we find the PGF for a discrete random. Okay, so PGF is non-negative integer valued random variable. Okay, then PX or PK, we actually use the general notation PK here for PGF. PK X equal, okay, probability that X equal to K or K equal to 0, 1, 2. Then the PGF G, the random variable X and a dummy variable S. This is defined as nothing but the summation over K from 0 to infinity and the probability that X equal to K and S, the dummy variable S to the power K. Okay, this is the definition for the probability generating function, and S lies within. Okay, so this is the definition how we calculate the PGF. There are some remarks, okay, like the first one is like the generating function value at s equal to 1. If you take the value of s equal to 1 here, then it is nothing but the summation of probability value. And we know that since it is a probability mass function, then it comes out to be 1. So sorry, I have written s here, but it comes out to be 1. Okay. Also, like the generating function is defined as actually, if you can see, s to the power k. Here as well, the expectation value of x is summation for discrete case. For discrete case, the expectation of x is defined as the summation over x probability function into the x only. Okay, so here x is replaced by s to the power k only. So it is also used like the PGF is defined as expected value of s to the power k. Also, the third one is like suppose gx of r. Here r is the rth order differentiation. Okay, that means dr upon dsr of the PGF is okay for r equal to 1, 2 up to so on. Then we can like define this at s equal to 1. I have written here in parentheses 1. So at s x equal to 1, small s equal to 1, this gives the actually factorial moment. Okay, so like these are called this particular quantity is called factorial moment, and like there are many distributions for which the variance is calculated with the help of the factorial moment only, like binomial. Even in binomial distribution we use the factorial moment, like use this particular concept to find the moment, second order or variance of the binomial distribution. Okay, also there is one more property, like we can, since the name of this generating function is probability generating function. Okay, so that means we can generate or obtain the probability with the help of this particular p generating function. And how it can be like calculated? So probability that x equal to k, suppose we want to calculate the probability of the random variable x at k, it is defined as actually gx. Okay, since at k, then it's a kth order differentiation. Okay, and then put the value of s equal to 0, and it is multiplied by 1 upon k factorial for k equals 1, 2, and so on. So this is how we calculate this. Also, like also the PGF is unique for all, like for every distribution there is unique PGF. Okay, probability generating function. Okay, that means if x and y have the same PGF, then this implies x and y are identically distributed. Okay, that means they have the same distribution. Okay, like in a similar, okay, we have example as well. Like suppose x is a discrete random variable. X is a discrete random variable, and we need to calculate the probability. Okay. And we are given the, not probability, actually we are given the probability mass function here. NCK p to the power k and q to the power n minus k. Here like k equals 0, 1, 2, and q is nothing but 1 minus p actually. Okay, and P lies between 0 to 1, excluding 0 and 1 both. So in that condition, okay, in that condition, the generating function, the probability generating function can be calculated as like this. NCK P to the power K Q to the power N minus K into SK. Okay, now you take P to the power K and S to the power K together, and then with the help of the binomial expansion formula, we can write like this. Now, since A plus B to the power N will be written like this, or P plus K. Okay, and then after that, P to the power K and S to the power K are taken together. So P S to the power K. So this comes out to be P S to the power K and plus Q whole to the power N. So this is the, okay, sorry. So this is the PGF. Actually, this is the PGF for binomial distribution, which we will discuss, I think, in the 4th or 5th week. Binomial. Okay. Now the second topic, the next topic is like the next topic is like MGF. Moment generating function. Okay, in short, MGF. Okay, so MGF is also like, suppose it is x is a random variable and expected value of e to the power tx exists for some t, for t in some interval, then the moment generative function denoted by mxt is defined as the expected value of e to the power ex. Here t is a dummy variable and x is the random variable. Okay, so we know that okay, this is the moment generating function only. Okay, also e to the power tx can be expanded, so this can also be like represented in this form: t upon 1 factorial expectation of x plus t square upon 2 factorial expectation of x square and dot t to the power n upon n factorial expectation of x to the power n. Okay, this is generated by the moments actually. Okay, and with the help of this moment generating function, we are able to generate moments, mean and variance can be calculated. Okay, these are we will discuss in the remark. So this is moment generating functions. The remarks are like this. Like the expectation of x to the power n. This can be calculated by differentiating the moment generating function with respect to t nth time, and at last putting the value of t equal to 0, then we are able to calculate the moments at that point. And this is a non-central moment. Here you can see that it is a non-central moment. So with the help of MGF, moment generating function, we are able to calculate the non-central moment by differentiating the moment generating function and putting the value of t equal to 0. So on. Okay. Also, MGF is also unique. Actually, there is a uniqueness theorem of PGF, uniqueness theorem of MGF is also there. Okay, so MGF is also unique. This implies, suppose we have two random variable x and y, and both follows the both have the similar form. Suppose, okay, then that means both follows the similar distribution as well. Okay, both are identically distributed. That means, okay. So yes, this is it. And the third one is also there. That's not the third remark. Actually, the third generating function is there. Okay, and this is characteristics function. Okay. Is actually defined as like psi. Okay. Sorry. Psi xt, the denotation or representation for the characteristics function, and is defined as similar to the moment generating function, but like this. The moment generating function is defined as the expected value of e to the power tx, and it is defined as the expected value of e to the power itx, where I is nothing but the iota, which is I equal to under root of -1. Okay. Now there are difference actually. Why we have defining three different since PGF is defined only for the random variables which are discrete in nature. Okay. Or that means which are non-negative integer valued random variables. For those random variables, we are able to define the probability generating function. And the MGF is valid for the random variable in which the expectation of e to the power tx exist is a finite for all t. Okay, just wait. Okay. MGF is valid for the random variable in which the expectation of e to the power tx is a finite for all t. Okay. In some interval including 0. Okay. The t variable, not like for all t belong. That means the t variable a some interval of t which includes 0. And for those only, we are able to calculate the moment generating function. But in characteristics function, since it is a like complex valued function, it is not like a real valued function. Here, like we define, it is a complex valued function actually. Okay, so the characteristic function has no restrictions. Okay, it can be defined in any way. So that's why we use three different, and these can be used in further classes also. So these are the things like we have discussed in up to third 3V. Okay. Again, like there is some remarks also. Let me write the remarks as well. Like the CGF at like psi xt at t equal to 0, the CGF comes out to be 1. Okay. Also, this value is bounded with 1 actually. The modulus value of phi xt is always either less than 1 or equal to 1. Okay. And also it is used to generate the or to calculate the moments as expected value of xn exist. Suppose if expectation of the expectation of xn exist, then it can be calculated with the help of the CGF as the nth order derivative of psi xt at t equal to 0 multiplied by 1 by I to the power n. Okay, so with the help of this, we can generate the expectation or moments when we are given the characteristics function. Also, the similarly, like characteristics function is unique as well, as we have discussed for PGF and for MGF. Okay, so these are like the topics we have covered in the third week. So if anyone have any doubts, or then they can ask, or then we will solve some question related to these topics. Okay. Then start with the question. Suppose we have a random variable. Suppose if x is a random variable. Okay. Then which of the options is incorrect for expected value of x and expected value of x square. Okay. For which we have given, like, there are 4 examples, 4 options actually. 1/2, 1/3. B is like 2 and 5. C is like 0 and 1. And D is like 2 and 3. So can anyone tell me how to solve this question? Like, we have the only information is x is a random variable. Either maybe it may discrete, it may continuous. This is not specify actually. And we are given the value of expectation of x and expectation of x square as well. So which of the following options is incorrect? Can anyone tell me how to proceed? Anyone? Okay. Let's see. Since we are given expectation of x and expectation of x square now, and we have discussed since variance is defined as expectation of x square minus expectation of x whole square. Okay. So, and also variance of x is either greater than or equal to 0. So let's check whether any of these 4 options violate this 2 properties or not. So let's start with A. Here, expectation of x equal to 1/2 and expectation of x square equal to 1/3. So variance of x is equal to what? 1/3 expectation of x. Okay, let me write in detail for first question. Expectation of x square minus expectation of x whole square. This implies expectation of x square 1/3 minus 1/2 whole square. This comes out to be 1/3 minus 1/4, and it comes out to be 1/12 actually. Okay, so it is greater than 0. So it is the correct one actually. So this option is correct one. Okay. Now option B, expectation of x is 2 and 5. Okay, 2 and expectation of x square equal to 5. Now again, everyone please try to solve by yourself as well and let me know the correct answer if you get the. Okay, so variance of x is like 5 minus 2 square, that comes out to be 1, which is greater than 0. So it is also the true one or correct one. The third one is expectation of x equal to 0, 0, and expectation of x square comes out to be 1. Again, variance of x equal to 1 minus 0 comes out to be 1 greater than 0. And the option D will be like expectation of x equal to 2 and 3. 2 and expectation of x square equal to 3. Here, variance of x equal to 3 minus 2 square, which is equal to minus 1, which is like not greater than 0, which violates the assumption for the variability. Okay, so this means option D is incorrect. Okay, I hope it's a very simple question. I'm just using the property of the variance to solve this. Okay. The next question will be like, we are given a PDF fx such that defined as 2x and 0, 2x when x lies between 0 to 1 and otherwise. Okay, so we need to calculate the expected value of x and variance of x. So everyone, please try to solve this and let me know the answer. Okay, we need to solve the expectation of x and the variance of x when the PDF is given like this. To solve and let me know. I'm also solving. So the expectation of x is defined as like this. it is defined as like, since it comes out to be like from 0 to 1, na, so the rest are actually comes out to be 0. So I'm directly writing it from 0 to 1. X into fx dx, 0 to 1, x into 2x dx, which is 2, x square dx, x cube upon 3, 0 to 1. Twice is here, it's 1 by 3, which comes out to be 2 by 3. This is the only expected value actually. Let me not write the answer here. Okay, the expected value of x comes out to be 2 by 3. Okay. Now, the next is variance of x. Variance of x is defined as like expectation of x square minus expectation of x whole square. Now, we don't know about the expectation of x square. The next step is to calculate the expectation of x square, which is defined as the 0 to 1 x square into fx dx, which is like 0 to 1 x square into 2x dx, which comes out to be 2 here, 0 to 1 x cube dx, twice x to the power 4 upon 4, 0 to 1. And after calculating, we'll get what? 2, 4, 8, and it comes out to be, okay, I think there is one mistake, no? Or everything is, I think, right. X square 4, okay. 2 is here, and 1 by 4, it comes out to be 2 by, it comes out to be 2 by 4, no, I think I have written 1 by 4 and 2 by 4, or 1 by 2. Okay, so the variance of x is 1 by 2 minus 2 by 3 whole square, comes out to be 1 by 2 minus 4 by 9, and after calculating 18, 9 minus 8, so variance of x comes out to be 1 by 18. Okay, and expected value of x comes out to be, okay, so just a simple question actually, how to calculate the mean and variance. Now we have one discrete type question as well. Like we are given the distribution like the value of x is 0, 1, 2, and 3, and the probability is suppose 0 0.5, 0 0.3, 0 0.15, and 0.05. Okay, now we need to calculate the mean and variance of random variable x. Okay, so again, the expectation of x will be defined as like, since it is a discrete random variable, so we may like write x from 0 to 3, x into probability that x equal to x. So like 0 into 0 0.5 plus 1 into 0 0.3 plus 2 into 0 0.15 plus 3 into 0 0.05 comes out to be 0 plus 0 0.3 plus 0 0.3 plus 0 0.15. So from here, the expectation of x comes out to be 3367.75. Okay, and what about the variance? Now again, we need to calculate the expectation of x square. which is defined at summation x from 0 to 3 x square, probability that x equal to x. This is the notation for PMF actually. So 0 square into 0.5 plus 1 square into 0.3 plus 2 square into 0.15 plus 3 square into 0.05. Okay, this comes out to be 0 plus 0.3 plus 0.60 and plus 0.45. So expected value of x square 9 and 13. Oh, sorry. 1.35. 1.35 is the expected of x square. Now the variance of x is calculated at expectation of x square minus expectation of x whole square. 1.35 minus, like we have, okay, 0.75 square, and after solution we get the final answer as 0.7875 as the variability. Okay, so this is the variance and this is the mean for this probability mass function. Okay, now the next question is like, okay, it's a lengthy question actually. We are given like the PDF as x to the power alpha minus 1, 1 minus x to the power beta minus 1, and this is beta function, beta function with parameter alpha beta. Okay, here like x lies between 0 to 1 and alpha and beta are positive quantity. Okay, so this is the PDF of a random variable x. Here like where beta function is defined as, here alpha beta is defined as like gamma alpha gamma beta upon gamma alpha plus beta. Okay, so this is the given PDF. We need to calculate the expected value of the random variable x. Okay, for which the given PDF is fx. So just try to solve this with the help of the definition. Okay, it's a quite some sort of lengthy, but let's try with yourself as well. So, okay, let's start. See, expectation of x is, since it is a continuous random variable, so it is 0 to 1 x into PDF. The PDF is x to the power alpha minus 1, 1 minus x to the power beta minus 1, and it is beta function with parameter alpha beta dx. This is the expectation of x. Okay, now if you can see beta alpha beta is a constant term, na? So we can like take it out from the integral sign, beta of alpha beta, and the integral is 0 to 1 x to the power 1 and x to the power alpha plus alpha minus 1 comes out to be x to the power alpha 1 minus x to the power beta minus 1 dx. Okay, so this is okay. Also, in mathematics, you people mostly know about the form of beta function. Okay, since like integral over 0 to 1 t to the power alpha minus 1 and 1 minus t to the power beta minus 1 dt. This comes out to be like beta function of alpha beta. Okay, now replacing alpha minus 1 with alpha. So we can write like this, na? This the last line. This star equation here we can write it like this, na? Beta alpha beta 0 to 1 x to the power alpha plus 1 minus 1 1 minus x to the power beta minus 1 dx. Okay, so comparing the red one and the blue one, we can write like this, na? 1 upon beta function with alpha beta into beta function with alpha plus 1 beta. Okay, now since beta function is already defined here, beta alpha beta is, suppose equation A is there, beta alpha beta is gamma beta upon alpha plus beta, gamma alpha plus beta. So solving this, so beta alpha plus 1 will be like gamma of alpha plus 1, gamma of beta, and divided by gamma of alpha plus 1 plus beta or alpha plus beta plus 1. And this is divided by gamma of alpha, gamma of beta, and divided by gamma of alpha plus beta. Okay. Also, we have one more property. Gamma functions have one more property, like gamma of alpha plus 1 is defined as alpha gamma alpha. Okay. Or some people say that it's alpha factorial. Okay. So look, we can write like this, na? This term alpha gamma alpha plus 1 will be written like alpha gamma beta and divided by alpha plus beta gamma alpha plus beta. We can write like this. Okay. And this is divided by this quantity, which is gamma alpha, gamma beta, and gamma of alpha plus beta. And after like cancelling the common terms, we will get the expectation of x as alpha upon alpha plus beta. Because like we can say here, na, this quantity, this quantity, this quantity are cancelling out. Okay, so the actual answer is alpha upon alpha plus beta. This is the first order or the expectation of x for which the given PDF is this. Okay, sorry, not this, this. Okay, again, we need to calculate the variance of x as well. Now, variance of x, which is defined as the expectation of x square minus expectation of x whole square. So expectation of x square, again, in a similar manner, we proceed. Okay, I'm not writing the whole step this time, but 0 to 1, x square, x to the power alpha minus 1, 1 minus x to the power beta minus 1 dx. Okay, and also divisible by beta of alpha beta, beta function of alpha beta, and beta alpha beta, and this can be like written as x to the power alpha plus 1, 1 minus x to the power beta plus 1 dx. And after solving like this, we get it like as this, no? Beta function of alpha plus 2 beta and divided by beta function of alpha and beta. And once you are going to simplify this, you will find the expected value of x square as alpha plus 1. I'm writing it directly. Okay, you may put the formula again. the numerator and denominator, and then after cancelling it out, the final जो simplified version है, that comes out to be like alpha plus beta plus 1 and alpha plus beta. Okay, this comes out to be the expectation of x square. Now variance of x will be alpha plus 1 divided by alpha plus beta plus 1 and alpha plus beta, and minus our expected value is like alpha square upon alpha plus beta square. So this can also be simplified. The final expression for the variance of x will be like alpha beta divided by alpha plus beta square and alpha plus beta plus 1. Okay, so this is the variance for the random variable x. Actually, this random variable is actually nothing but the beta distribution. Okay, this is a beta distribution which we generally use in like Bayesian analysis or even in classical as well. Okay, so it is a beta distribution, the PDF, and the mean and variance of the distribution we have already we have calculated now. Okay, suppose we have solved this for the arbitrary value of alpha and beta. For example, let's take alpha equal to 2 and beta equal to 3. For example, you may take any value. Then in that case, expectation of x will be like what? Alpha upon alpha plus beta. This comes out to be 2 upon 2 plus 3, comes out to be 2 by 5. Okay. And variance of x will be like, it's a long quantity. Okay. So I'm directly using the numbers here. Alpha into beta, that means 2 into 3 and divided by alpha plus beta whole square, 5 square, and multiplied by alpha plus beta plus 1, then 2 plus 3 plus 1, that comes out to be 6. So 6 divided by 5 square into 6 comes out to be 1 upon 5 square, which comes out to be actually 1 by 25. Okay, so then when we are given the particular value of the parameter, then we are able to calculate the expected value or the variance of those random variable in a numbers actually. Okay, so this is like moments and variance we have calculated. Now the next question is mainly based on the Chebyshev's inequality actually. Okay, so like we use different kind of formula na? For example, let me write here the formula. Probability that x minus mu is greater than or equal to k sigma. This is the same formula that we have read, 1 by k square, or we use this formula, or we use mod of x minus mu less than k sigma, okay, is greater than or equal to 1 minus 1 upon k square. Okay. This is the form for the Chebyshev's inequality. Also, some people may use the similar form with like replacing sigma from this point to that, from left side to right side. So you may also use those as well, like if you want to, but we may use this as well. Okay. So now the question is, find the set of values. Okay, for the set of values, let me write for the set of values, the percentage of values that lies within the population mean plus 3 standard deviation. okay, of population is what? Like we need to find the set of values, like we need to calculate the probability, how much probability lie within the mean value and the three standard deviation from the mean value. Okay. So again, we don't have the information regarding the distribution of the random variable. We only know about this. We have the whole information like this. The mean value and the standard deviation is maybe any quantity and three times. So actually, this is very well known one of the question. I will discuss after solving this question. Okay, so we have some examples even like some options here, like 83.75% is there. Okay, B is like 95% is there. C is like 88.89% is this, and D is like 99.73. Can anyone guess what will be the correct option? Okay, no problem. Okay, see, we have like Chebyshev's inequality in this form. So we use this form. Okay. So here we need to ask now the mean value. Okay. And the difference will be like 3 sigma limit. So that lies within 3 sigma limit. This implies x minus mu, the value of x will be like shifted from mu up to 3 sigma limit, up to 3 sigma distance like. Okay, so this quantity, since we use less than, so once we use less than, then is greater than or equal to 1 minus k square. Okay, so this probability is calculated by 1 minus 1 upon k square. Okay. And by comparing here k sigma, and here with sigma, we have the number 3 here. So this implies k equal to 3. So for, okay, let me write it here. After comparing, we get k equal to 3. Okay. Then this value equals 1 minus 1 upon 3 square comes out to be 8 by 9. So that means probability that x minus mu is less than 3 sigma is greater than 8 by 9. Or after solving this, you will find it is about to 88.89%. Okay. So 88 upon 89% of the data lie within this 3 sigma limit actually. Okay. So option second is the correct one. Sorry, option C is the right one. Okay. Also, if if you people know about the normal distribution, although we will discuss in, I think, in fifth week, but still, if someone knows about the normal distribution, then they may know the normal distribution is a bell-shaped or symmetrical in nature. And for normal distribution, the 3 sigma limit contain 99.73% of the data point. Okay. Like the option D is I'm writing here. The 99.73% of the data points lie within the 3 sigma limit, and those 3 sigma limit is defined as the mean value plus minus the 3 times of standard deviation of the random variable, which follows the normal distribution. Okay. So at least the minimum 88.89% of the time of the data set lie within this. Actually, this comes out to be the minimum value. It's a lower bound. Okay. So again, we have one more question. If anyone have any question, they may ask. Okay, I'm just solving one by one. Again, one question in the same manner. In any data set, suppose in any data set with 500 data points, what is the minimum what is the minimum number that lies what is the minimum number that must lie within 5 standard deviation? Okay, like we have 500 data sets actually. Okay, and now we need to find the minimum number that must lie within the 5 standard deviation. Okay, so 5 standard deviation of the mean. Sorry. Okay, again the similar question. Like we need to like x any random variable which may like shift from minus mu, and this quantity less than or equal to 5 times of standard deviation. Okay, again this is 1 minus 1 upon k square. Here k equal to 5. This implies 1 minus 1 upon k square equals nothing but 24 upon 25. Okay, so the probability that the point or the data set lie within the 5 sigma limit is 24 upon 25, which is very high. Now we need to find the number of data sets. Okay, so the number of data set or data point, the number of data point actually, the number of data point is 24 upon 25% or proportion of the data, that means the whole. And this comes out to be, can anyone tell me? 480, na? So 480 data set lie within the 5 sigma limit. Maybe you people have heard about the 6 sigma limit also. Okay, in which the maximum the millions of data, suppose we have a millions of data, and then a very few data lies behind the outside the 6 sigma limit. Okay, so this is how we solve the question related to the Chebyshev's inequality. We have now the next question, which is on the basis of moment generating function. Okay, now the question is, let x be a random variable with, we are given the moment generating function mxt as this, e to the power t by 2 plus e to the power minus t by 2 and whole divided by 2 and whole is square. Okay, for t is lying between minus infinity to plus infinity. Okay, now we need to calculate the probability. Now calculate probability that mod x greater than 2 by 3. Okay, we are given this moment generating function, and we need to calculate the probability that mod x is greater than under root of 2 by 3. Okay, so let's just start how like we proceed in the previous questions. Okay, we are given the mxt. Okay, we can like simplify the mxt even. So it's a square, so 1 by 4, 1 by 2 is there, so square 1 by 4, and e to the power like t by 2 plus e to the power minus t by 2. Okay, whole square. So a plus b whole square is also there. We may like use the formula. So let's just use, so 1 by 4 a square. Okay, so e to the power t. Okay, I think I have, okay, I think it's right. E to the power t plus e to, to the power minus t plus 2. Maybe I have missed some question or something. Okay, let's see then. Okay. Till then, our final expression will be like 1 by 4 e to the power t plus e to the power minus t plus 2. Okay. Now, we need to calculate the expectation. Okay, we need, wait. Okay, yes, we need to calculate this. Okay, this quantity we need to calculate. Okay, and this quantity, for we don't have any information, so we use some property of Chebyshev's inequality. Okay, and Chebyshev's inequality, for using the Chebyshev's inequality, we need the information about the expected value and the variance. Okay, so the first aim is to calculate the expectation and variance so that we can calculate the probability mentioned in star. Okay, so MXT is given, moment generating function is given, and we have discussed already the expected value of x from the moment generating function can be calculated with the differentiating the moment generating function one time and taking the dummy variable t equal to 0. So let's start the same thing, ddt of mxt at t equal to 0. Okay, so it's 1 by 4 is there. E to the power t is defined, the differentiation e to the power t minus e to the power minus t, because e to the power minus t is minus e to the power minus t, and plus minus comes out to be minus. Okay, so this comes out to be the expectation. And now when we put t equal to 0, then e to the power t comes out to be 1, and e to the power minus t comes out to be 1 as well, and 1 minus 1 equals 0. So the expected value of x for this random variable is 0. Okay, now we need to calculate the variance of x. So again, expectation of x square mxt d2 of dt2 mxt at t equal to 0. Okay, we need to calculate this. So it's 1 by 4 again. First order differentiation is already written in the above 41 page. Okay, first order differentiation is this. So 1 by 4 e to the power t and minus minus plus. Now plus e to the power t, e to the power minus t. And we are putting t equal to 0 again. So it comes out to be 1 plus 1, 2 to the power 2 by 4 or 1 by 2. So expectation of x square is 1 by 2 or 0.5. Okay, so now variance of x is 1 by 2 minus 0 square, that comes out to be like 1 by 2 only. So 1 by 2 is the variance. Now we have mean and we have variance. So with the help of the mean and the variance and using the Chebyshev's inequality, we are able to calculate the probability mentioned in star. So probability mod x. Okay, so probability like mod x minus mu is greater than 2 by 3 is less than or equal to variance of x upon 2 by 3. Okay, so from here we will find out variance of x is 1 by 2 into 3 by 2 comes out to be 3 by 4. Okay, so putting the values in the formula and after putting the variance and expected value, we will find the probability is 3 by 4. So probability that mod x greater than root 2 by 3 is less than or equal to 3 by 4. This is the final answer. So the maximum bound is 3/4. Okay. Now the next question is based on PGF, probability generating function. Like we have given, let x be a random variable. Let x be a random variable with probability mass function like hello. Am I audible now?
Yes, sir.
Yes, sir.
Okay, I think someone like wanted to ask something. Okay, so we are given this. We need to find the PGF. Okay, the fx of x will be like this: e to the power minus lambda, lambda to the power x upon x factorial, or lambda is greater than 0, x equal to 0, 1, 2, and so on. Okay. Actually, this is the PDF of a Poisson distribution. Okay, it is a discrete type of distribution, Poisson distribution. So here, since we have not like read till now the Poisson distribution, we are given the PDF, a random PDF suppose, and we need to calculate the probability generating function. Sorry, we need to construct the, not calculate, the construct the probability generating function. So, and with the help of those probability generating function, we calculate the mean and variance of the random variable as well. So, okay, let's start. Look, look, the probability generating function is defined as like expected value of s to the power k, if you remember, or x to the power s. Okay, s to the power x. This is the how the PGF defined. Since it is a discrete random variable, so we like write k from 0 to infinity, because for in Poisson distribution, x may vary from 0, 1 to up to infinity. Okay, so expectation of s to the power x is s to the power x, probability that x equal to x. Okay, so writing down k equal to 0 to infinity, s to the power x, then PDF is e to the power lambda, lambda to the power x upon x factorial. Okay, now okay, let me write on the next page. Okay, e to the power lambda is constant actually, so we have taken it common. So we have summation k from 0 to infinity s to the power x, lambda to the power x. This may written as s lambda to the power x upon x factorial. Maybe you know the summation over s lambda to the power x upon x factorial is nothing but the expansion of e to the power s lambda. Okay, so from there we can write it e to the power lambda, e to the power like s lambda. Okay, here it is minus lambda, na? E to the power minus lambda is there actually. Okay, so please correct it. E to the power minus lambda, e to the power sx, or after simplification we get e to the power minus lambda and 1 minus s. Okay, this is the PGF or probability generating function for the random variable x, which have probability mass function as fx is equal to e to the power minus lambda, lambda to the power x upon x factorial. Okay, so we have calculated the PGF. Now, with the help of the PGF, we need to calculate the mean and variance of the random variable. Okay, so okay, so expectation of x is actually defined as gx at s equal to 1. Okay, we have discussed in the remark actually this. Okay, and expectation of x square. is defined as G double dash, like 2 times 1 into, sorry, not into, it's plus G prime X at this. Okay, the expectation of X is defined as this, and where expectation of X square can be calculated with the help of G double prime plus G prime at S equal to 1. So we first calculate these two terms, and after this, we will calculate the variance as well. So Gx prime S comes out to be e to the power minus lambda, like dds of e to the power minus lambda 1 minus S. Okay, so first e to the power minus lambda 1 minus S, and then minus minus plus lambda S is also there actually. Okay. Yes, I think this is the right one. Lambda S is there. G prime S. Not lambda. Okay, sorry. And lambda into S, then when we differentiate lambda S with S, then it comes out to be lambda only. Na? So lambda into e to the power minus lambda 1 minus S. This is the PGF. Now Gx prime of S at S equal to 1 comes out to be e to the power minus lambda 1 minus S into lambda at S equal to 1. So 1 e to the power 1 minus S, and it comes out to be e to the power 0, which comes out to be 1 finally. So the lambda. Okay, and this is nothing but the expected value of X. Now G double prime X equal to, now this comes out to be like e to the power minus lambda e to the power minus lambda 1 minus S into lambda, which is lambda square e to the power minus lambda 1 minus S. Now G x double prime at S equal to 0 equal to like lambda square e to the power minus S 1 minus S at S is equal to 1, not 0, sorry again. So this comes out to be lambda square. Okay, so expectation of X square is G double prime plus G prime. Okay, so lambda square plus lambda. And the variance of X is defined as the expectation of X square plus expectation of X whole square. So this comes out to be expectation of X square minus expectation of X whole square. This comes out to be variance of X is lambda. Okay, so variance of X is lambda on expectation of X is also lambda, and it is a Poisson distribution in which the mean and variance have the same value, and which is equal to its parameter. Okay. So up to this point, anyone have any question? Hello.
No, sir.
Okay. Suppose.
Sir, could you
Okay.
just down the slide just a little bit?
Yes.
Sir, I just want to see that. Oh, it's. Thank you, sir.
Okay. Look, we have operate the similar question and calculate the MGF as well. Okay, we use the PGF, probability generating function, and with the help of this PGF, that here, okay, with the help of this PGF, we are able to calculate the mean and variance of the distribution. Okay, and now the next question will be like the same question. Okay, suppose X equal to X will be like e to the power minus lambda to the power X upon X factorial, for X equals 0, 1, 2, and so on. And lambda is greater. Okay. Now we need to calculate the construct the MGF. Okay. find moment generating function. Okay, so again, MXT will be like summation, summation x from 0 to infinity e to the power Ex and PF. PDF is like e to the power minus lambda, lambda to the power x upon x factorial. Okay, so again, e to the power minus lambda is taken common. Okay, and the summation x e to the power Tx and lambda to the power x. So that means e to the power t into lambda whole to the power x and divided by the power x factorial. Okay, again, this is nothing but e to the power lambda, and this quantity, the summation quantity e to the power t into lambda. Okay, so this is the extension of e to the power t lambda. So after simplifying, we will get e to the power minus lambda. Suppose we'll take minus lambda as a common, 1 minus e to the power. So the MXT will be like e to the power minus lambda, 1 minus e to the power t. Okay, so this is t for all t, because for any value of t, this MXT is defined actually. Okay, so this is the MXT. Now, with the help of this MXT, we can able to calculate the moments as well. Like for example, expectation of x, which is equal to defined as the first order differentiation of MXT with respect to t, and then put the value of t equal to 0. So here e to the power minus lambda, 1 minus e to the power t is there, and then t into e to the power t is also there. So it comes out to be lambda e to the power t. Okay, now putting t equal to 0. Putting t equal to 0. See, if we put that value of t equal to 0, this quantity, the first one, this quantity comes out to be 1. E to the power t also comes out to be 1. Only lambda is there. If you can like simplify this, I'm writing it directly actually. You people may understand, na? Like here, e to the power t, e to the power 0 comes out to be 1. Then 1 minus 1, 0, e to the power 0, this whole quantity comes out to be 1. Okay. In a similar manner, e to the power t, 1, e to the power 0, 1 into lambda, that means lambda. So whole quantity comes out to be lambda. Okay. So expectation of x is lambda, and also now expectation of x square. This is second order derivative mxt divided by, sorry, and at x square at t equal to 0. Now we need to define this quantity. This quantity with respect to differentiate this quantity with respect to t again. So it comes out to be, the first one is like since it is a two function, na, fx into gx, so we need to use like a product rule. So the first function is lambda e to the power t, and suppose if you take any value lambda e to the power t and some other values, so lambda e to the power t and then e to the power minus lambda 1 minus e to the power t plus lambda e to the power t into e to the power, let me write it, into e to the power minus lambda 1 minus e to the power t into lambda e to the power t. So it comes out to be square actually. Now at t equal to 0, if again we put the value of t equal to 0, it comes out to be like lambda plus lambda square. After solving, we will get lambda plus lambda square. Let me show you how. Okay, this quantity comes out to be like 0. So e to the power comes out to be 1. Then this quantity also comes out to be 1. So lambda from here, this point, and then here lambda square is there actually, because the whole lambda e to power t whole square, so lambda square is also there. Okay. So then we have expectation of x square as well. Now the variance of x is lambda plus lambda expectation of x square, which is lambda plus lambda square, minus expectation of x whole square, which is minus lambda square, comes out to be lambda. So from the PGF and from the moment generating function, we can calculate the expectation and the variance of a distribution with the PDF or PMF, PDF actually, with PMF this. Okay, and this is nothing but the Poisson distribution with lambda parameter. Okay, we will discuss it in, I think, next week. Then we will discussing about the spatial discrete distribution. Then it is one of the most used distribution. Okay, so these are the cases. So, like, is there any questions? Because I have completed all the questions. So if anyone have any doubt, then he or she may ask, or then if not, we can conclude our session here. Anyone?
Sir, could you just refer me book which should I use to solve the questions?
Okay. Look, there are lots of books actually. Like you may solve V.K. Rohit's book is there. Okay. Even Dharmaraj sir have already written a book.
Yes, sir.
I don't have. Yes.
The
You don't
first
have
book
the
you
PDF.
mentioned is
Okay, V.K. Rohit.
no, sir.
Sorry, please ask again. I don't like understand.
I did said that I didn't hear your voice while you are mentioning the book name.
Okay. Look, okay, I will write some PDF, some book. I'm also like provided the PDF of the book in the drive. Okay, you people have the access of the drive, na? You people have drive access,
Yes,
na? I think I have, yes. Then I will like download 2 or 3 books in that drive, and from there you can access the question related to these topics. Okay. Is it okay, na?
Yes, sir, it's okay. Thank you, sir.
Anyone else? Okay, then if there is no question, then let's complete this session here only. Okay, thank you, everyone. Let me stop the recording.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you. You people may leave.